Hey, are you ready for Chapter 2? What do you mean no? Okay, we're going to do it anyway. Okay, Chapter 2 in this portion of the book all starts with basically following the OSI model. So this is all about Layer 1, the physical layer. And the learning objectives are actually pretty cool, so let's take a peek at those. And it says, you need to know the functions of the physical layer. You know, what physical medium is and why copper and fiber optics are cool. What signals are and why are they necessary. Examples of signals, and then examples of multiplexing. So that's what we're here to learn today. Okay, so let's start from the beginning. So the functions of Layer 1. It's to provide the signaling, okay, which is kind of a roundabout circular argument, but bear with me, it'll make some sense. So signaling provides transparent transmission of a stream of data over a circuit. Yeah, okay, that's a little heavy-handed. Some sort of a circuit built from some physical communication medium. Yeah. Basically what it means is it converts data into signals. That's the bottom line. Okay, there's a figure 2.1. So I've got some sort of data, whatever it is, and I need to transform it into a signal to be able to send it over the wire. So this is my wire, this is my Ethernet cable, and I'm expecting -5 volts or +5 volts. I have to take data, whatever that data is, and convert it to voltage. So data to voltage is what this whole thing is about. This is that physical layer. Okay, and the takeaway behind all this is kind of weird, so just relax and pay attention. Data cannot be sent over wires. Alright, I'll say that again. You can't send data over wires. You can only send signals over wires. Okay? This is a fundamental concept and probably subject of test questions. So data obviously can be converted into signals, which is what Layer 1 is. This is what Layer 1's designed to do. If somebody said, why the heck do we even have a Layer 1? The answer would be to convert data into signals. Okay, cool. Because once again, some digital representation has to turn into voltage. And that's what Layer 1 does for me. Okay, that's pretty cool. So if signaling is transparent transmission of blah, 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 what the heck is a signal? And so a signal, in its simplest terms, I'll use the definition in the book, but it's a little funky. A detectable transmitted energy that can be used to carry information. Okay, so basically we're talking about some sort of transmission of energy, and typically we're talking voltage, unless we're talking about fiber optic cable, and then we're off into a different discussion. But most of the time we're talking about voltage. You know, the voltage goes up or down, or there's a waveform on the wire. And so detectable energy that can be used to carry information. Most of the time voltage. There's a little section there on page 43 that talks about the special features of this. So of all of the layers in the OSI model, this is the only one that has to deal with the real world. In other words, this is the only one that has to worry about temperature and humidity and, lightning strike. This is the only one that has to deal with, honest to God, things that you can touch. I can't touch my Layer 2 or my Layer 3, but I can certainly touch the Layer 1 guy. Okay, so let's talk about some of the limitations in the physical world. So copper, for example, is typically used to transmit power to your house, and signals through the cables and stuff. And it's a very cheap metal. There's a little diagram in the book that talks about how the price of copper is very plentiful. It's not like it's a rare metal. It's fairly relatively cheap. The price kind of goes up and down a bit, but hey, it's not bad. It has kind of an inherent bandwidth. There is because of it's the properties of the metal itself. There is about a 1 gigabit per second limitation, and we'll discuss what that means in a little bit later. And depending on the physical size of the wire, if you made the wire really, really thin, it'd be really cool, but if you put too much power through it, it would heat up. So if you made it really, really thick, then it would be immune to being, heating up and losing power, but it would be, huge and weigh a ton. So there's lots of trade-offs you have to deal with how to build a wire. Noise, electrical pulses going down a wire tend to leak, and they tend to pick up noise from surrounding surfaces. Shielding, bin radius, can you just take a fiber wire, and tighten a knot? Can you do that? Or will it break? Well, copper, most likely, the wire is small enough that you can actually get away with tying it into a knot. I wouldn't try that with a fiber optic cable, but you can get pretty doggone creative. So these are the things we talk about that have to deal with the physical world. On page 44, they talk about, again, the physical media and the types of physical media that they're out there. And so pay attention. Twisted pair. This is typically things like phone cords and Ethernet cables are these twisted pair stuff. Coaxial cable, which could be the old style Ethernet from a long time ago, or cable TV, that kind of thing. Fiber optic, which is used for almost everything for long distance telephone operations, that kind of stuff. And then all sorts of radios and funky things like, they have infrared and laser and radio and all these other things. Now there's two categories of these guys. One is called guided media. Now guided media basically means it has to follow along a particular path. So now we're talking about wires and fiber optic cable. Those two are guided. The radio, the infrared, and laser, those aren't really called guided. So if I'm talking about a wire, and I put that in quotation marks, wire, I'm typically talking about guided media because I really want to include fiber optic. If it's a thing, a cable that I connect to one end, a cable I connect to the other end, a cable is a cable, therefore it's guided media. If it doesn't have a cable, it ain't guided media. Okay. They kind of dig a little deeper. On page 46, they go into a little bit more detail about copper wire. The first one they talk about is unshielded twisted pair, UTP, unshielded twisted pair. This is a category. They have category 1, 2, 3, 4, 5, 6, 7, and most people just pronounce it cat. So this is like a cat 3 cable here. This is a cat 5 cable here. And basically, the higher the category, the more data carrying capability it has. So you might notice that twisted pair, you can see that like for example, these have little twists in them, and this is good stuff. It's designed to nullify the noise. Let's say, for example, if I had a plus 5 voltage and a minus 5 voltage I was sending over a wire, and I got a little noise in there. By twisting the cables together, the noise could be mathematically erased, so to speak. So by twisting the pairs, I can make it more immune to noise. I'm not going to go into the physics of it all, but just trust me, twisting the pairs makes it not necessarily more immune. It provides a easy and cheap way for the device manufacturers to try to erase noise. Okay, you've heard of noise canceling headsets and things like that. Have an earphone that's noise canceling. That's not what we're talking about. We're talking about, it still gets the noise, but we just have a way of making it less important. In the old days, the category 3 stuff is basically what the phones use, essentially. And it has about 3 or 4 twists per foot. And the book says that category 5 has 2 or 3 twists per inch. And I'm thinking, dude, no. Those guys are smoking dope. That's not the way it works. And in fact, there is no standard for the number of twists per foot in a cable. That doesn't exist. So each manufacturer is allowed basically to do their own thing. And I will tell you, again, I'm not trying to get into the physics of it all, but typical high quality category 5 and maybe a 5E cable, each one of the pairs in there have a different number of twists. This one might have, 5 twists per inch. This one might have 3. This one might have 4.5. They don't all have the same number of twists. And again, this has to do with their ability to selectively pull out noise. So the book is a little wrong. Shielding. Now this does not have a shield. Well, it has a mechanical shield. It's got a plastic Teflon cable, sheathing on the outside that's designed to keep the thing from rubbing. Basically, the Teflon on the outside is designed to make this thing pull through like conduits and things like that. But you could get another kind that has a foil or a wire mesh on the inside. And the way you do this is you'd run this from point A to point B, and then you would like ground that portion of the shielding, and it'll help. Now, most people don't have that kind of problem. But let's say, for example, I worked at a radio station, okay, and I'm 50 feet from the radio tower, and it's a 1,000-watt radio tower. I'm probably going to get an awful lot of EM, electromagnetic noise on everything, absolutely everything, and therefore I might, in that strange scenario, I might want to use shielded twisted pair. Okay. Once again, they talk about the UDP categories. So every category is designed to provide you a little bit better transmitting capability. Category 3, about 10 megabits per second, Mbps. Cat 5E, E stands for enhanced. Basically got you somewhere in the 1 gigabit range. And then category 6 is 10 gig. There's actually one they're working on kind of sort of now. I mean, it's available. It's not really an official standard, but you can call it Cat 7. And it's for very, very short period, very, very short cables. We're not talking about, 100 meters. We're talking, 10 meter distances. But anyway, the takeaway behind this is, as the category goes up, so does the maximum data rate. That's the cool takeaway. The next thing they talk about is this guy. This is an RJ45, an 8-pin connector. RJ stands for registered jack. It's just a little doodad that sticks on the end of the wire. And if this was not a face-to-face class, one of the things I would have you do is I'd be passing out wire in a little crimper, and you try your hand at lining up all the wires and stick it in there into the crimper and going chink, and then we test the cable to see how well you did. Believe me, if this is the first time you've done it, you'll probably not get it right. It's not that it's physically difficult to do or line up thing. It's just that you need practice, because half the time you think, oh well, I've got the brown and the white brown right there, and you stick it in there, and then no, it twists when you put it in. Okay, so RJ45. So 8 wires in here, which mean 4 pairs of wires. So here's what those 4 pairs look like. So this is kind of looking on edge. So there's pairs, and they have 1 pair in the middle and 1 pair on the outside, and then 1 pair on this end and 1 pair on that end. So those are the 4 pairs and how it works out. So here's a good Trivial Pursuit question. In a typical 10 meg Ethernet cable, are all 8 wires actually being used? Let's take a peek. The answer is no. In the 100 meg range, pair 1 and pair 4 are not actually being used. Kind of weird, huh? However, if you're going up to 1 gigabit, well, then they are. And then there's the other one called PoE, Power over Ethernet, and all this is they take advantage of the fact that there's pairs that are available, so they can send voltage over the wire. And you only use that for things like if you have a voice over IP phone and you don't want to have a power cord. So your Ethernet jack is your data and your power at the same time. Okay, we've reached the 15-minute mark, so we'll pause right here and pick this thing up again in just a few.